Hello everyone, our project is a community autonomous remote speed sensor, and my name is Jugal and I worked on this project with my team members Inioluwa, Adnan and Meharpreet. Our client was Jason Russell from Tomorrow Foundation. Tomorrow Foundation is an Edmonton environmental charity with a mission to build connected, equitable communities and increase local environmental understanding. The driving force behind our project stems from a critical concern: the fact that people speed in residential areas poses a significant risk to community safety. With this in mind, Tomorrow Foundation started an initiative to enhance community well-being by offering an open-source, accessible solution, a remote speed sensor. We worked with Tomorrow Foundation, and our goal was to empower community members to take action towards safer roads. By deploying this remote speed sensor, individuals can contribute towards a safer environment for everyone. We aim to deliver an affordable yet effective tool that easily integrates into community life. We envisioned a system where users could easily deploy the sensor and access real-time data through a user-friendly website. The essence of our project lies in its simplicity and accessibility. Our system rose to the challenges, successfully meeting these expectations. Not only does it provide the essential functionalities of speed measurement and timestamping, but it also offers user flexibility to access and interpret data remotely. Furthermore, we also incorporated different operational modes to allow for power-saving opportunities. In summary, our project embodies Tomorrow Foundation's commitment to safety and empowerment. Through diligent efforts and innovative solutions, we have created a tool that not only addresses the pressing issue of speeding but also fosters a sense of shared responsibility and collaboration within the community.
This is a monitoring unit. The primary component in a prototype is the Doppler radio sensor. It emits microwave radiations at a frequency of 24 GHz, which then gets reflected from moving objects. It has an independent transmitting and receiving route, has an operating distance of 15 meters, and can operate in temperature ranging from -20 to +60 degrees Celsius. It outputs analog signal with voltage in the range of -300 to +300 millivolts. Connected to the sensor is the amplifier circuit. The amplifier circuit has a gain of 10 and outputs a voltage of 5 volts peak to peak. The output of the amplifier circuit is in the form of a square wave, which denotes the Doppler shift frequency. The waveform is sampled and processed by the Arduino Uno to determine the velocity of passing vehicles. The Arduino also filters noise and attempts to ensure that only valid motion is recorded. The Arduino then sends over the recorded speed values to the ESP32 via UART interface. The ESP32 actively aggregates and timestamps the recorded data. Depending on the mode of operation of a device, it either sends to the backend server right away or it batches data to save network bandwidth. We also have a second ESP32, which is responsible for establishing connection with the mobile app via Bluetooth. In our current design, it is only active during initial configuration of a new device and receives config info like the Wi-Fi SSID and password from the user to get a new device up and running. The two ESP32s interface via UART. Our device regularly sends heartbeat messages to the backend server every 5 seconds to ensure remote monitoring and configuration of the device by the admin.
What worked? We set very high targets for ourselves in the project with the aim to achieve the majority of functional and performance requirements and even surpass them in ways possible. Some of the aspects that worked well include measuring the speed of vehicles accurately. To test the accuracy of our device, we compared the speed recorded by device with those recorded by a speed gun. The obtained result matched closely, indicating a high level of accuracy for our prototype. The device also timestamps the recorded speed measurements to the nearest minute, and it integrates well with our cloud infrastructure. Furthermore, our prototype saves network bandwidth and reduces power consumption by sending the recorded data in batches to the cloud server. Additionally, the device can operate continuously without requiring any human intervention after the initial configuration and setup. The device allows easy user configuration via Bluetooth and Wi-Fi using the car's mobile application. The application enables the admin user to get operation feedback on the device, whether the device is reachable or not. We assume that the device is reachable if it has communicated with the server in the last 5 minutes. The aspects that did not work include solar power. We wanted the device to use solar power so it could have a greener power supply and improve its capability to operate without interruptions. We did not attempt to integrate this because of time constraints. The other limitation of our prototype is that it cannot identify the direction of recorded vehicles. Having this capability would allow us to retrieve more insights from the recorded data.
This slide summarizes the budget of our final prototype. It consists of our key components, including the two ESP microcontrollers, the Arduino, the Doppler speed sensor, our power source, the rechargeable battery, and some other components. Now that we have decided to use separate ESP microcontrollers for the Wi-Fi and Bluetooth functionality, the additional ESP has contributed to the change from our last budget update. Additionally, we have excluded some of our other components that have not been included in our final prototype, like the speakers and casing. As we can see, the total cost comes to about $95, which is well under the original prototype budget of $400. Additionally, we can also estimate that the manufacturing cost per unit would be a little less, and this would still remain under the goal of $200. Future work. This slide outlines some of the biggest potential avenues for development of a final prototype of the CARS project. A major area for future development is enhancing the robustness of data security and privacy. We plan to use OAuth, which ensures secure token-based authentication, enabling users access to external applications or websites without having to share their credentials or personal information. Additionally, we can consider incorporating AES-256 encryption, which would serve to protect data by making it unreadable without the correct decryption key, ensuring that even if data is intercepted or accessed without authorization, it remains secure. Moreover, we can adopt TLS for data that is being transmitted between the device, the app, and the cloud server, which would provide a secure communication channel, safeguarding against eavesdropping and tampering. These security measures would not only enhance the overall safety of the system, but also build user trust in the CARS system. Next, we want to optimize our size, weight and power, and cost. Currently, our setup uses two ESP microcontrollers and an Arduino Uno. The Arduino serves to convert the Doppler waves to readable speed, and additionally, it serves the operating voltage limitations imposed by the Doppler sensor amplifier circuit. However, to initially set up the device via mobile Bluetooth connection and then send the captured speeds via local Wi-Fi, we require Bluetooth and Wi-Fi modules. This is provided by the ESP microcontroller, but due to a shortage of programmable memory, we had to use two, one to implement the Bluetooth-related functionality and the other for Wi-Fi-related jobs. We believe utilizing a single microcontroller that meets the operating voltage requirements and possesses both Wi-Fi and Bluetooth modules will significantly reduce the size, weight, and power consumption of our prototype. This would also reduce the cost of the prototype and additionally remove the need for inter-microcontroller communications, thus improving the device's performance and efficiency. We also want to leave room for advanced functional capabilities, and in this section we look forward to potentially adding a machine learning model to analyze traffic patterns. This could help us predict where dangerous speeding might happen and identify risk zones, so communities may possibly take proactive initiatives to prevent it. These improvements may significantly strengthen the security, efficiency, and utility of the CARS system.
In summary, the CARS project showcases the impact of engineering innovation on addressing important societal issues. Through teamwork, we designed, developed, and tested a prototype that meets our main goals and reflects our vision of using technology for the public good. The success of this project isn't just about the working prototype, it's also about its potential to make communities safer. Cars offers communities data that can be used to push for necessary changes, such as using new traffic calming measures, making neighborhoods safer.
Starting.
Do you see anything updated?
It's just coming.
Oh, let's go! Oh, this guy's too fast, bro. Too fast. Too fast. 46!
Oh!
And this is our website where community members can visualize the data. So this is our homepage. Let's get right into it. User comes in and selects the device. So let's say this is an example of a device that we were using to collect speed data, and it gives me the device ID and it also gives me the device location. I hit confirm, and if I hit all, I will be able to see all the speed data that was collected by this speed sensor mapped against the time. And if I go to the live speed, I can view the last speed that this sensor captured, which was 13 kilometers per hour, April 11th at 6:55 p.m.
Okay, here we go. Focus. Speed. I am speed. One winner, 42 losers. I eat losers for breakfast. Breakfast? Maybe I should have had breakfast. A little brekkie could be good for me. No, stay focused. Speed. I'm faster than fast, quicker than quick. I am lightning.
Good job! Now have to work on another capstone this semester.